We will now talk about the planets and their atmospheres, and in particular on their influence on the physical conditions on the surface of a planet. The Earth, Venus, and Mars are, for example, three very similar planets, yet their atmosphere are very different, as well as the meteorological features on their surfaces. We will see in a simplified manner how the energy budget of a planet, namely the balance between received and emitted energy, completely determines the physical conditions on the surface, and therefore may be the development of life. For example, on Venus, the greenhouse effect is such that the surface temperature is completely determined by atmospheric physics, and the atmosphere is so opaque to radiation that only radar imaging is able to unveil the surface of the planet, such as on this picture taken by NASA's Magellan probe. To understand the influence of planetary atmospheres on their planet, let us have a look at the energy budget of each planet, in particular the Earth. We have here a simplified representation of the solar system. The Sun is here. The Earth is here. And here we have another planet, Saturn, for example. The Earth is, of course, at 1 astronomical unit away from the Sun, and Saturn, or any other planet, is at a distance d. We will now look at the energy budget. What is the energy received by planets? And what is the energy emitted by planets? First, the energy received on Earth. The energy received at the top of the atmosphere can be measured, for example, by satellites, and is called the solar constant. The solar constant, S, is an energy flux, or more accurately, a power flux, the numerical value of which is 1.37 10^6 ERG divided by cm square S. Since the solar energy is diluted, spread over a sphere with a surface of 4 pi times the square of 1 astronomical unit, at a distance d, namely the distance d here, SD is the solar energy, S integrated on a sphere with a surface of 4 pi, times the square of 1 astronomical unit, 4 pi d Earth. So this is the square of 1 astronomical unit, and diluted on a sphere with a surface of 4 pi d square. We have then here 1 divided by 4 pi d square. Finally, S, d, is simply a rescaling of S by a factor d, Earth, divided by d square. We have just seen the energy received by the Earth. Now let's have a look at the full energy balance for the Earth. We have some energy here that is absorbed, which we just talked about. It is the energy flux coming from the Sun. We have some emitted energy, which is the energy produced by the planet itself, for example, due to radioactivity in the mantle or the terrestrial crust. Finally, there is some radiated energy. This radiated energy is due to the black body radiation. ECN here is a black body radiation. If we observe the Earth from outside of the solar system and measure its spectrum, we will see a black body spectrum. What is now the energy balance? There is the solar flux, which is absorbed energy, and there is energy emitted directly by the Earth. Their sum must be equal to the black body energy, the one we observe from outside the solar system, the energy that an outside observer would receive. We rewrite the absorbed energy as a function of the solar constant. It is equal to the solar constant times the Earth's cross-section. It is the energy received on Earth. The Earth's cross-section is pi r square. Obviously, only a part of the light is absorbed, and the rest is reflected. We express this with the factor 1 minus A, where A is called the albedo. If A equals 1, then all the radiation is reflected. And if A equals 0, all of it is absorbed. For the Earth, A equals 0, 3. So we have an absorption radiation plus an emitted radiation, of which we are going to talk later, equal to the blackbody radiation. As we just wrote, the absorbed radiation is pi times the radius of the Earth squared, namely the cross-section, times the solar constant, times 1 minus the albedo. The emitted radiation, which can, for example, be produced by the liquid magma under the terrestrial crust and its radioactivity, is the surface of the Earth. 4 pi r, Earth square, times Q, the produced energy, by this radioactivity, say at ground level. We can measure the value of Q and find 0.06 W divided by m square at ground level. We multiply Q by the factor 4 pi r square to get the total energy emitted by Earth at ground level. Now, what about the energy radiated as blackbody radiation? As we saw in the lecture on the black body, a black body emits an energy flux depending on its temperature, sigma T 4. So we have sigma T 4, T being the effective temperature of the black body. We have to multiply this by the total surface radiating this flux, which is simply 4 pi times the Earth's radius squared. This gives the complete energy balance. Let us rewrite this equation in a slightly different manner. So we have the absorbed energy plus the emitted energy is the blackbody energy. If we rearrange the different terms, we end up with the following equation. So we have 4 sigma T 4 with T the effective temperature, which is actually the parameter we are interested in, over 1 minus A S. For the Earth, A equals 0, 3, which means that 30% of the light is reflected. We also had that Q equals 0.06 W divided by m square at the Earth's surface. The solar constant, S, on the terrestrial orbit is S equals 137, 10, and 6 ERG divided by cm square S. If we plug all these numbers in this equation, we get that the blackbody temperature of the Earth is 255 Kelvin. Note that this is the Earth's blackbody effective temperature, and not the temperature at ground level, which is completely dominated by the climatology, by Earth's atmosphere. We just saw that the Earth behaves like a black body. We have the Earth with an atmosphere acting as a filter. We have on the one hand the incoming radiation from the sun, which is UV and visible light, and on the other hand the outgoing radiation, which is infrared light. Since we have a black body with a temperature of 255 Kelvin, which peaks in the infrared domain. On one side, we have the UV radiation. If I draw here the emitted or received flux on Earth as a function of the wavelength, we have a blackbody curve. So this is a black body at a temperature of 5,780 Kelvin, namely the sun. This is some radiation with a peak in the UV optical according to Wien's law, and it is an incoming radiation. We have, therefore, an incoming UV optical radiation which attempts to pass through the Earth's atmosphere, acting itself as a filter. The Earth itself, as we just computed, emits blackbody radiation with a curve of the same shape, but this time with a blackbody temperature of 255 Kelvin. The Earth emits then in the infrared domain, and this is the outgoing radiation. What happens in the atmosphere? We show here as a function of the altitude and of the wavelength the different filters blocking the several kinds of radiation. First, in the upper atmosphere, at an altitude of 10 kilometers, we have water molecules and ozone molecules. At ground level, up to a few hundred meters, or a few kilometers high, we have CO2 particles, as well, of course, some water. There is also water quite high in the atmosphere. It could be water created by burning of kerosene, by the engines of airplanes. So here we have water produced by airplanes, and water naturally present at ground level. On the ground, the CO2 is partly caused by cars. This is here an ozone layer that CFC can destroy. If we consider all of these together, we have UV light that enters the atmosphere, which could be blocked by the ozone layer. But if the ozone has been destroyed, it cannot filter this radiation. If the ozone has been destroyed, the UV radiation can penetrate all the way to ground level because there are no more natural filters. UV light is blocked by ozone. If the ozone layer is destroyed, UV radiation can enter the atmosphere and thus contribute to warming the Earth. This obviously applies to any other planet, which has incoming and outgoing radiation, with several filters either at ground level or at high altitude. We have then UV light blocked by ozone, which is not blocked if the ozone layer has been destroyed, and we have an infrared outgoing radiation. This outgoing radiation could naturally escape if there is no filter such as CO2, which indeed blocks infrared. As a result, there is less outgoing radiation than there should, and some energy is retained at ground level by the CO2, as well as by the water at high altitude. Water also being an infrared filter. Water is naturally found at ground level, but not at high altitude. Water ejected by the burning of kerosene by airplane motors acts like a filter blocking the outgoing infrared radiation. This shows that the climate we know on Earth and the greenhouse effect on Earth are due to the sun's temperature, the Earth's blackbody radiation, and the chemical composition of the atmosphere, which is either natural or artificially altered by mankind and sets up a number of filters, blocking incoming or outgoing radiation. There is a natural equilibrium unless any change is imposed by human activities. This equilibrium can be broken, for example, by adding filters here, water and CO2, or by destroying filters, protecting it from the incoming ultraviolet radiation. Let us see a few numbers about the influences on the surface temperature of a planet. If we take Venus, the Earth, and Mars as example, we see that the solar constant decreases with the distance, but not the blackbody temperatures, due to the quite different albedos of the planets, and due to the small amount of intrinsic energy produced. However, the surface temperature varies heavily, due to the presence of an atmosphere, regulating the energy fluxes between a planet and the rest of the universe.